Hello, my name is Dr. A.J. Coomer, PhD. I am the smartest mathematician who's ever lived. We are reading Euclid's Elements Book 1, Proposition 7. I have not looked at this. I did try to read I glanced at this, and I didn't understand what the hell was going on, so we'll have to see. Here, let me zoom in. So, given two straight lines constructed from the ends of a straight line and meeting in a point, there cannot be constructed from the ends of the same straight line and on the same side of it two other straight lines meeting in another point and equal to the former two respectively, namely each. Okay, so it's describing a situation and saying that it's impossible. Right? There cannot be constructed. Okay. What? If possible, given two straight lines AC and CB constructed on the straight line AB and meeting at the point C. Okay? Let two other straight lines AD and DB be constructed on the same straight line AB on the same side of it. So we haven't, again, this is kind of where I'm like sympathetic to Weilberg, because I think defining these things algebraically, like how do you define the side of a line? Well, you can do that algebraically with signed areas, but okay, whatever. On the same side of it, meeting in another point D equal to the former two respectively. So, namely, each equal to that from the same end, so that AC equals AD, which has the same end A. CB equals CD. Oh, is this side congruence of triangles? CB equals DB, okay, which has the same end B. Join CD. Since AC equals AD, therefore the angle ACD equals the angle ADC. Right, it's an isosceles triangle. Therefore the angle ADC is greater than the angle DCB. Why? It cites 1.5. What was 1.5? So AC equals AD. Right. So therefore the angle ADC is greater than the angle DCB. Right, because DC. Okay. See, I'm a little bit confused because, again, we're doing geometrical constructions and then sort of making these weird, almost algebraic arguments. Again, 300 BC, so whatever. Therefore, the angle CDB is much greater than the angle DCB. DCB. ADC is greater than the angle DCB. Okay. CDB is much. Okay. Right, okay. Okay, so this is what was confusing me. I didn't quite. Right. Okay, so here, this is why I think the algebraic framework. I gotta develop. I gotta just write all this out. Honestly, the algebraic framework is superior. Um, I just right. I gotta work on that. Okay. So here. So there's a question here. Let me actually. Should I open GeoGebra? Let's open GeoGebra. We're just doing geometry, right? So blank piece of paper. Okay, let's make a line segment AB. Okay, and now, and oh well. And let's make a circle here. And let me zoom in on this so that you can see it. I don't know if it will actually zoom in. Okay, so we have A, B, C, and D. And then what I want to do, I want to make this circle. I want it to be obvious that there is a circle there. Okay. Let's zoom out again. Okay, so we want. So he's saying the angle ACD equals ADC. Okay, so let's measure those two angles just to make sure that we're on the right track here. Where is the angle measurement tool? Okay, so we want the angle ACD ADC. Nope. 80 degrees. Okay, and then okay, so they're either going to be okay. The point is that these two angles are always the same because it's an isosceles triangle. Okay. Is there a way for me to always select an interior angle? I don't know. Okay. Okay, since AC equals AD, the angle ACD equals the angle ADC. And let me just zoom in so that you can see what's going on. So here, these two angles are always equal, no matter what, because it's an isosceles triangle. Therefore, the angle ADC is greater than DCB. Okay, so let's measure that angle, DCB. Now, I think, let me delete this. So here it's 80 degrees. Okay. But if D is inside the circle, no. Okay, I see. Even if we were measuring the other angle, this angle is clearly... Okay, that makes sense. But again, since CB equals DB, okay, so now we got, let's do another circle. Nope. Okay, there's two intersections for these circles, so there's the boring intersection of these two circles, but let's pick the interesting intersection. First of all, let's make this let's construct this intersection down here. Yeah, let's just move it. Okay, so now we maybe have an interesting... Okay, if possible, given two straight lines AC... So let's try to read what this says again. Given two straight lines constructed from the ends of a straight line and meeting in a point on the same side of it. Okay, so that eliminates this case down here. Right, so basically I think maybe what he's saying is that circles meet in so in maybe our modern terminology, you have 2-degree 2 equations, two circles, and they're going to meet, they're either the same circle, in which case they meet in infinitely many points, but assuming AB is non-zero, these two circles are going to meet in exactly 2 points, one of which is going to be on top of this, they're going to be on different sides of the line segment. Okay. That's maybe what he's saying, and he's saying so. Okay, so yeah, so if I maybe, let me gray this out for a moment. God damn it. Son of a bitch. Why do I have the drawing pad? I'm not drawing right now. Okay, so if I gray this out, right, it is true that these two triangles are these two triangles are congruent down here and only down here. Otherwise, so it's not possible to make, So is this just the side-side-side congruence theorem, I think? Or it's saying the side-side-side equality theorem, and then the only, I don't know, something about... So again, if I'm doing this, I'm going to construct this algebraically. Anyway. Okay. So let's move this over here. So what's his argument? So since AC equals AD, therefore the angle ACD equals the angle ADC. So this isosceles triangle, okay. Let me maybe make this a lighter or a darker. Let's make this like a green. There, that's a good blue. No, blue, there's not enough contrast. red, maybe an orange. Okay, well, we'll just live with red for now. Okay. So CD. And the angle tool. The angle tool in GeoGebra, you are perfectly useless. Quit constructing points, please. Okay, since AC equals AD, therefore the angle ACD equals the angle ADC, right? So because of equilateral triangles, or isosceles triangles. Therefore the angle ADC is greater than the angle DCB. Therefore the angle ADC is greater than the angle DCB. And so this is where we were getting into trouble, because that's not true if we're like here. And so maybe, right, so here, so here there's no way to construct one of these points inside the triangle, but if we do this, and then our original one, let's make that black, and let's make the other one like green. No. Okay, and these angles are just ridiculous. Okay, so let's try to make it here. Where's the grid? Grid. I want the grid just so that we can construct something that kind of looks like what we were doing. And these light, this needs to be a darker color. It's a purple and a purple. Okay, and let me just zoom in. Nope. So this is the setup. We have a triangle ABC, and then we have this point D. And what Euclid is trying to show, I think, is that basically that if we make now this right, maybe that a better way to phrase it is the only congruent triangle. The only triangle that is congruent to the purple triangle is this blue triangle that happens to meet down here. But again, his proof has this issue, which is where, so as long as this is the situation, I think the proof works. That's what he said. That's what the notes say, is that as long as we're in this situation, the proof works. But if B is like way over here, let's say, and let's say put A down here, okay? Now I can break the logic of the proof by putting D inside of the circle. Right, and I think that's an issue. Okay. So let me zoom out again. KDE has this zooming feature. I don't know if it's showing up on OBS. Anyway. Okay. Since AC equals AD, ADC is greater than the angle DCB. Therefore, the angle CDB much greater than the angle DCB. Again, since CB equals DB, does. Oh, okay. Right, okay. So basically these two circles only intersect in these 2 points. That's the problem is, so the problem here is that we're constructing an impossible situation and then proving that it's impossible, and so it's just inherently hard to visualize an impossible situation. Okay, since CB equals DB, therefore the angle CDB also equals the angle DCB. But it was also proved CB equals DB. Okay, because so what he's saying, so let's imagine that D is down here, and we're going to violate one of the original premises, which was that we're on the same side of this line. Okay, this is the only construction that's kind of close, but what he's saying is that, okay, suppose that you construct a new point that is equidistant to A and equidistant to B as C. So, in other words, it lies on the intersection of these two circles. So these two gray circles that hopefully you can see. Lies on the intersection of these two gray circles that you can hopefully see. Okay? So it has to be the same distance from A and the same distance from B. Okay. In that case, he's doing some weird convoluted proof to prove that there are exactly two, well, I don't think he says there are exactly 2 points, but there are exactly 2 points where these two circles meet. And if you restrict yourself to only being on one side of the line segment, he doesn't define side, but there is a way to do that with signed areas. So I think I'm going to write like a thing on just like very basic algebraic, like rational geometry. I think I got to write my QAnal book, and I got to get serious about doing that. All right. And I got to do an outline. Anyway. Since CB equals DB, therefore the angle CDB also equals the angle DCB, which is also CB equals DB. So right, okay. So let's actually move. Let's move this point C to being very far away. Okay. What is he saying? CDB so CB equals DB. That's the only way to make that work. See, yeah, again, it's because he doesn't. Okay, I'm criticizing one of the greatest mathematicians of all time, but this proof sucks. Hmm. And there's all these weird properties of angles that he's not. CB equals DB, therefore the angle CDB also equals the angle. Given two straight, okay. Okay, I understand what he's saying. So what he's properly saying is that if we do if we make these two circles, they only meet in 2 points, and then if you further restrict yourself to they have to meet on the same side of the line, there's only 1 point where they meet. That's I think the better way of saying this. But he's not saying that circles meet in either 2, 1, or infinitely many points. Because you can have circles that are like tangent to each other. Or, you know, again, in rational geometry, we have all these problems with, you know, solving equations. Anyway. In order to conclude the angle ADC is greater than the angle DCB, it's necessary for the angle ADC to be greater than the angle DCB. No shit. But that won't happen unless the point D lies outside the triangle ABC. So let's zoom in. And let me put the axes there, and let's put these on. Let's put A at the origin, and let's put B at 10. And let's put C at okay. Okay, and let's turn off the axes. I think the axes are obnoxious. Okay, and so, right, so here was the problem, which is that if we put C way the fuck up here, let's say. Okay, now, oh no, what we want B to be way the fuck over here. Now, and let's move C down. Now we have the problem, which is that ADC is greater than the angle DCB. ADC. Okay, let's just compare these angles. Let's compare the angles. Angle. We want positive orientation, so from okay, and then ADC is greater. So can we cook up a circumstance? This is Euclid Book 1, Prop 7. Why can't I grab? Okay, I'm just gonna close, save. Okay, I'm again confused. So Euclid frequently treats only one case. So I actually do want to figure out if we can cook up a counterexample. Open recent. Sorry, I think GeoGebra had a bug in it. Okay. So GeoGebra angle tool. Why are you so bad at what you do? I want the interior angle here. So DCB. Really? Really? You're going to be like that today. Okay. The angle ADC is greater than the angle DCB. It is necessary the angle ADC to be greater than the angle DCB, but that won't happen unless the point D lies outside the triangle. So let's put it inside the triangle. And once again, of course, GeoGebra has decided that today is fuck with AJ day. DCB. I can't get it to be bigger. So what am I missing? Maybe if I move it like maybe let's just go like really fucking extreme. Like no, it's always bigger. That's the problem. Oh, maybe you know what we could do is we could get D. Yeah, so if we got D down here, okay, let me construct the other. Hmm. Because I bet we could come up with. Yeah, again, if we follow the rules, then I think Euclid is right. Hmm. So let's look at the hidden justifications. Yeah, so I just don't understand this at all. Oh well. Hidden justifications, the sentences. The angle ACD equals the angle ADC. Therefore, the angle ADC is greater than the angle DCB. Okay, so uses several properties of magnitudes. ACD, ADC, DCB. CN5 justifies the unstated angle ACD greater than DCB since DCB is part of ACD. Yeah, I'm just getting like I can't. These three-letter words, I just get my brain just melts. Anyway, this if x is greater than y and y is equal to z, then x is greater than or x is less than z. Sure. Transitivity, right? Not listed as a common notion. Okay, so transitivity and whatnot. These are not listed as common notions, even though they probably should be. As in the proof of the last proposition and many to come, the law of trichotomy is also used. Here it's used to reach the final contradiction. Yeah, I am just lost. I don't understand. It's side 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 congruence. So maybe the way I'm going to phrase this is two circles meet. I'm going to say two circles almost always circles meet how do I phrase it? I don't know. Something about how circles meet. That's a much cleaner way to phrase this anyway. All right. So if I phrase it as, yeah, okay. Maybe I'm going to try to figure out a way to phrase this in a rational way. I don't know. I'll see you. Bye. Founder loves you.